Welcome, everyone. Today we are embarking on a fascinating journey through the evolution of AI software. We will explore how we have transitioned from simple, stateless API calls to dynamic, autonomous agentic systems. Let's get started. To understand the dawn of the agentic era, we must first define what makes an AI agentic. Traditional generative AI is highly reactive. It waits for your prompt, generates text or an image, and stops. You can think of Gen AI as being all talk. Agentic AI, however, is all action. It doesn't just respond, it decides what steps to take, makes plans, and changes its approach if something fails. We are shifting from systems that require micromanagement at every step to systems where we simply define an outcome and let the AI determine the path. This represents a monumental leap in software evolution. Looking at this diagram, you can clearly see the fundamental difference between traditional Gen AI and agentic AI. On the top path, the workflow is strictly linear. A human provides a prompt, the AI generates an output, and the process terminates. It is entirely reactive. On the bottom path, we see the agentic approach. A human provides a high-level goal, and the AI enters an iterative loop. It plans, acts by using external tools, observes the results of those actions, and adapts its plan if necessary. This loop continues until the final outcome is achieved, demonstrating true operational autonomy. Before we can appreciate autonomous systems, we must understand our baseline. Historically, software interaction, including early LLM usage, was completely stateless and linear. A traditional LLM is essentially a static predictor. It generates the next token based on a prompt, drawing only on patterns encoded in its training data. If you needed facts from outside that training data, you as the human developer had to write code to make an API call, parse the response, and feed it back to the model. The AI itself had no memory, no feedback loop, and no ability to interact with the environment. It was entirely confined to what it already knew. This flowchart visualizes the traditional software architecture. The user input triggers the application logic, which is hard-coded by a human developer. The application makes a direct API call, retrieves the data, formats it, and then passes it as a static prompt to the LLM. The LLM simply processes that prompt and returns a static response. Notice that the application logic, the human-written code, is doing all the heavy lifting and orchestration. The AI is merely a passive processing node at the very end of the pipeline, completely blind to the larger workflow. The evolutionary leap from an API caller to an autonomous agent requires one critical ingredient: state. To move from static predictions to a dynamic system, we must give the LLM a memory-bearing process. We do this by implementing concepts like finite state machines, which track exactly what the system knows at a given moment. By persisting the conversation and tracking progress markers, the agent can reuse earlier results in later turns without starting from scratch. This addition of short-term and long-term memory transforms the AI from a reactive tool into a persistent entity capable of sustained, intelligent support across complex workflows. Here we see a visual representation of a stateful agent workflow. Unlike the linear pipeline we saw previously, this is an iterative loop. The agent begins in a planning state. Once it decides on an approach, it transitions to acting. Crucially, the results of that action are stored in memory. The agent then transitions to a reflecting state, where it retrieves this new context. Based on this reflection, it either loops back to planning to adjust its strategy, or, if the goal is achieved, it terminates successfully. This memory-driven cycle is the heartbeat of autonomy. Now that our AI has a memory and a state, it needs hands. This is where tool-augmented LLMs come into play. Agency truly emerges when internal reasoning is coupled with concrete external actions. Instead of a developer hard-coding an API call, we bind a suite of tools directly to the LLM and allow the model to decide whether and which tool to call. For example, if tasked with financial analysis, the agent can autonomously call a web search tool for live stock prices, pass that to a calculator tool, and synthesize the result. Modern AI models are explicitly trained for this, transforming them from mere text generators into active participants in digital ecosystems. This diagram illustrates the tool augmentation process. At the center is the agent core, powered by the LLM. When it encounters a knowledge gap, it sends a structured request to the tool router. The router dispatches this to the appropriate external system, be it a web search, a Python code execution environment, or a SQL database. These tools execute the command and return an observation back to the agent core. The agent integrates this this new, real-world data into its reasoning process, effectively bridging the gap between its static training data and live, dynamic environments. To bring memory and tools together, we use frameworks like React, which stands for Reasoning and Action. An agent that only reasons never accomplishes anything, and an agent that only acts cannot learn from its environment. React solves this by forcing the AI to think out loud. The agent generates a reasoning trace of thought about what to do next before it takes an action. Once the tool returns an observation, the agent reflects on it. The magic here is that this entire internal monologue becomes part of the agent's state. This recursive process allows the agent to self-correct on the fly and provides us, the human operators, with a transparent audit trail of its decision-making process. Let's walk through the React loop. The cycle begins with a task input. The agent first generates a thought, a logical assessment of what is needed. Based on this thought, it executes an action, such as calling an API. The environment returns an observation. The agent then evaluates, is the goal met? If no, it routes back to a new thought, incorporating the previous observation to refine its strategy. It loops through thought, action, and observation iteratively until the goal is achieved, finally producing the final output. It is continuous, autonomous problem solving. Just as human professionals eventually meet their limits on massive projects, a single AI agent can only take a workflow so far before complexity demands coordination. To scale up, we move to multi-agent systems, or MAS. Instead of relying on one generalist agent, we deploy a team of specialized agents, perhaps one dedicated to web scraping, another to writing code, and a third to reviewing output. We orchestrate these teams using specific architectures. In a supervisor model, a central agent acts like a manager, delegating tasks to workers and synthesizing the final result. By dividing and conquering, MAS can iteratively solve highly complex enterprise-level tasks that would overwhelm a standalone model. This diagram showcases a classic supervisor architecture in a multi-agent system. The user request hits the supervisor agent first. The supervisor analyzes the overarching goal and breaks it down, delegating specific subtasks to specialized worker agents, a research agent, a data agent, and a writing agent. These specialized workers process their individual tasks and return their specialized outputs back to the supervisor. The supervisor then integrates all these pieces together, ensuring alignment, and delivers a highly polished, synthesized final output to the user. As we grant software the power to act autonomously, we must urgently address risk. We are not aiming for chaotic, unconstrained systems. Instead, we design for orchestrated autonomy. Agents are constrained by the workflow's permissions and safeguards we provide. A critical component of this is the human-in-the-loop, or HITL mechanism. When an agent is about to perform an irreversible or high-stakes action, like executing a financial transaction or sending a client email, the system pauses. It creates an approval gate, presenting its intended action to a human for review. Far from slowing the system down, this oversight is exactly what makes Agentic AI safe and viable for real-world enterprise deployment. This flowchart demonstrates a human-in-the-loop safety mechanism. When the agent plans an action, the system checks if it is a high-risk operation. If it is low risk, the tool executes immediately. However, if it is high risk, the workflow is interrupted, and the proposed action enters a human review gate. The human operator can approve the action, allowing execution, or reject and edit the proposal. If rejected, the feedback is sent back to the agent, which then replans its approach. This ensures humans retain ultimate control over critical outcomes. To conclude, let's look at the profound paradigm shift this evolution brings: the move from apps to agents. Traditional applications are passive containers. They require you, the human, to provide all the context, click the buttons, and manually move data between silos. Agentic AI flips this model. In the near future, the agent, not the web browser, becomes your primary interface. You will simply state an intention, like plan a business trip. An ecosystem of autonomous agents will negotiate with airline APIs, check your calendar, and handle expenses in the background. We are moving from a world where we micromanage software to a world where we delegate goals to intelligent, autonomous systems. Our final diagram contrasts the old world with the new. On the left, the app-centric model. The user must manually interact with the UI, clicking and typing to drive singular API calls. The burden of orchestration falls entirely on the human. On the right, the agentic model. The user simply provides an intent to an agent interface. The agent takes over, autonomously orchestrating communication across multiple disparate APIs, flights, calendars, and expenses to achieve the holistic goal. This is the future of software, from manual API calls to seamless autonomous orchestration.